Opportunity to share our work. I'm excited to be here, or there, as it were. I feel like I should start with an apology, though. I feel somewhat underdressed for the occasion in this informal t-shirt, but I definitely promise that I'm wearing the nicest pair of pants that I own. So that makes up for this old t-shirt. Let me also just take this opportunity to encourage any and all questions. Please don't hesitate to interrupt me if something's unclear. Naive questions are especially welcome. I care more about answering your questions than showing you whatever is on the last slide of the presentation, so don't hold back. So as you might have figured out, I'm going to be discussing disentangling, interacting, fermionic symmetry-protected topological phases of matter. And this talk is based on work that was done in collaboration with Yuan and Nat, and they deserve their own slide. Arguably, they deserve more than one slide. Here's Yuan Chen, and here's Nat. Yuan is a postdoc now at the University of Maryland, and Nat is a postdoc. He has the knowledge of a postdoc. Nat is a graduate student at Harvard. And a possibly more appropriate title for this slide is, if after the next 50 minutes of me waving my hands in the air, nothing makes sense, then these are the people that you should talk to. They know what they're talking about, and I've learned a lot from them working on this project. Let me also acknowledge Lucas and Sujit. I worked with Lucas and Sujit on earlier versions of some of the models that I described, that I will describe. This is the most important slide in my talk. Let me now move to the second most important slide in the talk, which is some motivation. I'll be discussing fermionic symmetry-protected topological phases, or fermionic SPT phases. And some notable examples of fermionic SPT phases are topological insulators and topological superconductors. Fermionic SPT phases have been well studied under the assumption that the interactions between the electrons or the constituent fermions are weak. In this case, the problem reduces to solving a single particle Hamiltonian, and consequently, non-interacting fermionic SPT phases have been thoroughly classified. But this begs the question, what happens to the classification of fermionic SPT phases in the presence of interactions? And new tools are needed because you have to deal with the full many-body Hilbert space. In fact, the phases of matter that I'd like to discuss are intrinsically interacting. There is no free fermionic representative of these phases of matter. Let me comment on two strategies for dealing with interacting fermionic SPT phases, and they're complementary strategies. The first approach is to use field theory. We can reduce the complexity of the problem by simply studying the low energy effective field theory of the fermionic SPT phases. This allows us to still extract the universal properties of fermionic SPT phases. And complementary to that, another approach is to identify exactly solvable microscopic models. And that's the approach that I'll describe in this talk. The motivation here is, one, it's a proof of concept. It shows that the universal properties predicted by field theory can indeed emerge from some microscopic picture. And second, and maybe this is hopeful, if we have an exactly solvable microscopic model, then maybe this is the first step towards an experimental realization of some of these intrinsically interacting fermionic SPT phases. So moving forward, things are about to get more abstract. But let me just mention, I have an anchor here. This is experimental evidence of a topological insulator in 3 dimensions. And it also serves as motivation. Again, potentially these exactly solvable microscopic models will help lead us to an experimental realization of these interesting phases. So this is the second most important slide of the talk. Let me move on to the third most important slide of the talk. The importance of the slides in the talk roughly decays with the duration of the talk, so plan your coffee drinking accordingly. Let me talk about what I'm going to talk about. I put fermionic symmetry-protected topological phases in the title of the talk. So I assume there's some self-selection in who actually showed up to this thing. But Nonetheless, I'd like to start by defining fermionic SPT phases. And I'm going to give a quantum information inspired definition for fermionic SPT phases. In particular, I'm going to define fermionic SPT phases in terms of finite depth quantum circuits. And finite depth quantum circuits will be useful throughout the talk. So this also gives me an opportunity to define finite depth quantum circuits. All of our Hamiltonians and their ground states can be written explicitly in terms of finite depth quantum circuits. After defining fermionic SPT phases, I'm going to narrow the focus of the talk to supercohomology phases in 3 spatial dimensions. These are examples of intrinsically interacting fermionic SPT phases. Again, by that I mean there is no free fermionic representative for these phases of matter. That makes it especially valuable to have microscopic models describing the supercohomology phases. So I'll introduce our construction of supercohomology models and try to emphasize one of the main benefits of our supercohomology models, which is our supercohomology models allow for an easy, relatively easy extraction of the universal properties that characterize supercohomology SPT phases through probing with symmetry defects. Namely, I'll show that, and I'll drape some more words around this later, I'll show that for supercohomology phases, symmetry fractionalizes in a certain sense on the fermion parity flux loops. And this is a key characteristic of supercohomology phases and can be seen somewhat immediately from our construction of supercohomology models. Then, if there's time, I'll discuss our construction of supercohomology models on a manifold with boundary. These models host an anomalous topological order at the boundary. And I'll conclude by listing some open questions. So as promised, a definition of fermionic SPT phases. I'd like to first note that fermionic SPT phases are always protected by a fermion parity symmetry. This is a consequence of requiring the Hamiltonian to be local. If you were to include a term in the Hamiltonian with an odd number of creation and annihilation operators, then that would in some sense be non-local, given the commutation relations between, or anti-commutation relations between creation and annihilation operators. Therefore, any reasonable local fermionic Hamiltonian will be fermion parity even. I'll represent the fermion parity symmetry by Z2F. Now, unless otherwise stated, I'm going to assume that the total protecting symmetry of the fermionic SPT forms a product. So of the form GF is equal to G, which is a finite unitary group, times fermion parity. Many of our results can be extended to more general symmetry groups, but just to avoid addressing caveats, ifs, ands, and buts, I'm going to focus on symmetry groups of this form. With that, I can define fermionic SPT phases using finite depth quantum circuits. A finite depth quantum circuit is a unitary operator that emits a decomposition into local unitaries, sometimes referred to as gates. The gates can be further organized into layers, and the depth of the circuit is given by the number of layers. By finite depth, I implicitly mean that the depth of the circuit is constant with the system size. Here I have drawn here a finite depth quantum circuit acting on a one-dimensional system. We'll be interested in three-dimensional systems, but I can't seem to draw quantum circuits in 4 dimensions very well, so I'll let you fill in the extra 2 dimensions. Now with finite depth quantum circuits, there's a working definition for fermionic SPT phases in terms of quantum states. The particular states we're interested in satisfy the following 3 properties, and I'll refer to them as GSPT states or GFSPT states. First, they're the ground state of some gapped local parent Hamiltonian. Second, they're short-range entangled, meaning they can be constructed from an unentangled state by a finite depth quantum circuit. And third, they're G-symmetric. So these properties define GFSPT states. Here's an artist's rendition, not a very good artist, here's an artist's rendition of the set of GF-SPT states. We define...
Can I interrupt with a very simple question on a previous slide?
Absolutely.
What is a finite depth circuit? So as you say, it's constant depth in the size of the system.
That's
but
right.
Presumably the depth diverges depending on the accuracy with which you want to get a certain state, even though it's independent of system size.
That's right. I'm being a little bit misleading here. Ultimately, a precise definition of fermionic SPT phases might use unitaries which are generated by some local Hamiltonian. I can always approximate that unitary operator with a finite depth quantum circuit. So this is really a working definition. So more precisely, we define SPT phases with any unitary operator that can be generated by a sufficiently local Hamiltonian. And the translation...
suppose I want to get a certain wave function.
Right.
With exactly, wouldn't I need an infinite number of infinite depth quantum circuit or a local Hamiltonian with an infinite number of terms?
So any symmetry-protected topological state can be prepared by the finite time evolution of some local Hamiltonian. It may be
but the local
that
Hamiltonian must have an infinite number of terms. They may be exponentially decaying, but it must have an infinite number of terms. How can you get it exactly otherwise?
It may be that in order to represent that with a quantum circuit, you need an infinite depth circuit. But in fact, for all the SPT states that I'll show, and for all but a set of measure 0, they can actually be prepared by a finite depth quantum circuit.
Yeah, but those, no, I mean, maybe just go back to what you mean by a local Hamiltonian. Is the local Hamiltonian allowed to have an infinite number of terms with an exponentially decaying interaction in space?
That's a good question. I don't have that precise of a definition of SPT phases. In my mind, I usually think of local as the terms are strictly supported on some bounded region, but you could include these tails. And in this work here, they include finite time evolution by local Hamiltonians, where the terms in that Hamiltonian might have exponentially decaying tails, or even tails that decay faster than any power.
Isn't the issue kind of similar, sorry to butt in, to how you can represent states with finite correlation length by MPS with still some fixed finite bond dimension in one dimension?
I think that's a fair analogy, yeah. You may not be able to exactly represent.
I think that's a separate thing. No, I think the point is more that a generic gap state is never truly an MPS, right? The point is just that if you're okay with capturing local quantities with some fixed but small error that is exponentially small, some variable, that in that variable you want, like for any fixed, as you scale the depth, you get the errors of observables to be exponentially small in that depth.
Yes.
Yeah, well, the same is true for these quantum circuits, right? If you want to only locally approximate observables to some accuracy, then you can in fact use a finite depth quantum circuit.
Exactly.
Oh, okay, so it seems we all agree that as the accuracy goes to becomes perfect, the depth becomes infinite.
Sure, yeah.
All right, thank you.
Yeah, sorry if that was unclear. So we have this set of GSPT states. We're going to impose an equivalence relation, and that'll allow us to define fermionic symmetry-protected topological phases. The equivalence relation we impose is the following. We call two GF-SPT states equivalent if you can construct one from the other by applying a finite depth quantum circuit composed of symmetric gates. Each gate in this finite depth quantum circuit has to commute with the full GF symmetry. The result of this equivalence relation is a partitioning of the set of GSPT states into equivalence classes into fermionic SPT phases. And an important question one can ask is, what is the classification of the fermionic SPT phases in this picture? I'm going to address something slightly different. I'm going to work with a known classification, namely, it's a partial classification given by group supercohomology. What I'm going to show you is a construction of a representative wave function and a representative exactly solvable model within that supercohomology phase in 3+1 dimensions. And what's especially nice about these models is that they'll allow us to analyze the universal properties of supercohomology phases in from probing with symmetry defects. So in what's to follow, I'm going to give a somewhat precise definition of the relevant supercohomology data, and then I'll give the construction of our supercohomology models. But before I do that, let me pause and give myself some water. Are there any questions, comments, concerns, background Zoom noises?
You have the word disentangling in your title. I was wondering if you could explain that.
Yeah, so that's a reference to the finite-depth quantum circuits here. And the SPT states that we can write down can be disentangled. They can be turned into a product state by applying a finite-depth quantum circuit.
Oh, I see.
It's also a play on words because it's like sorting out supercohomology phases. It's like disentangling them.
Mm-hmm.
It's funny, and I assume there's uproarious laughter right now. I just can't hear it because everyone's muted.
I think it also means that the quantum circuit may not satisfy any symmetry to disentangle SPT phase. There's a symmetry requirement. I mean, the quantum circuit, if it have a symmetry, you cannot disentangle SPT state. If a quantum circuit don't have a symmetry, you can disentangle any SPT state.
Right, so I'm not sure if I caught all of that, but the non-trivial SPT states, by definition, can't be constructed from a product state by symmetric gates, by symmetric local unitaries. You require some unitaries which don't commute with the symmetry. Otherwise, by definition, they'd be trivial under this equivalence relation.
Yeah, it was symmetric, yeah.
So there's something special here. Yeah. Now there's some additional meaning to disentangling, and if I remember later in the talk, I'll try and mention it. Okay, let me say a few words about supercohomology phases. Now, this is the most abstract slide in the presentation, but if we can make it through this slide, I think we'll be able to make it through to the end of the talk. Fermionic SPT phases in 3 spatial dimensions are partially classified by group supercohomology. Group supercohomology was originally derived by identifying retriangulation invariant partition functions. The precise origin of group supercohomology and the corresponding supercohomology data won't be necessary to fully understand for what's to come. I've tried to craft the rest of the presentation so I can just give a working definition of the supercohomology data. Nonetheless, let me start with a high-level description of the supercohomology data and then give the bare minimum that's needed going forwards. So here's the more high-level definition of the relevant supercohomology data, which classifies or gives a partial classification of fermionic SPT phases in 3 dimensions. The group supercohomology data is composed of 2 group cocycles, or group cochains. Rho is a 3-group cocycle with coefficients valued in Z2. And nu, let me just a second. Your faces are over my screen and I need to move you. And nu is a 4 cochain with coefficients in U1. Furthermore, rho and nu, this pair, satisfy the so-called Gu-Wen equations, meaning that rho is closed. It satisfies d rho equals 0. And d nu is equal to -1 to the rho cup 1 rho. where rho cup 1 rho is some algebraic operation at the level of cochains, which won't be important to describe here. Furthermore, the supercohomology data satisfies some equivalence relations, which I won't make explicit here. That's the high-level explanation of supercohomology data, and I put it in a black box here metaphorically. Moving forwards, here's what we'll need. We'll need that rho is some function from 4 copies of G to Z2, and nu is some function of 5 copies of G to U1. For those that are familiar with these things, I'm using the homogeneous notation here. So rho and nu are symmetric in their arguments. With this, I can describe the construction of our supercohomology models. So the main idea here is that I'll take a set of supercohomology data. It's this pair of functions, rho and nu, and from it, construct an exactly solvable model. That means I'll construct a representative wave function, a finite-depth quantum circuit, a kind of special finite-depth quantum circuit that prepares that wave function from an unentangled state, and an exactly solvable Hamiltonian. And again, I want to emphasize this. What's special about our supercohomology models is that you can easily characterize the phase by its responses to probing with symmetry defects. Again, you can characterize the phase by probing it with fermion parity defects. Before I move on to describe the construction of our supercohomology models, let me pause and see if there are any questions, comments, concerns, virtual yawns.
Tyler, just to clarify, this G is not GF. This is straight up G.
That's right. This is straight up G.
Okay, thanks.
Yeah, that's important. All right. So to define our supercohomology models, I need to first introduce the Hilbert space. And second, I'd like to say a few words about the fermionic operator algebra. Our supercohomology models can be defined on an arbitrary triangulation of an orientable 3-manifold. We also require that this triangulation comes equipped with a branching structure. Here I've drawn just 2 tetrahedra of some larger 3-manifold. I'm assuming that it's a closed manifold right now. And the branching structure, just as a reminder, is an assignment of an orientation to each edge in the triangulation in such a way that there are no closed cycles around any of the faces. At this point, the branching structure does 2 things for us. First, it gives us a local ordering of the vertices. We can order the vertices by the number of edges pointing towards the vertex. So here, this vertex has 0 edges pointing towards it. It's the first in the ordering. This one's the second, third, and fourth. Second, the branching structure gives us an orientation for each of the tetrahedra. So here I've chosen a convention where this tetrahedron is positively oriented, OT equals +1, and this tetrahedron is negatively oriented, OT equals -1. We define a Hilbert space by assigning a G-spin degree of freedom. This has the dimension equal to the order of the group G to each vertex of the triangulation. At this point, a basis state can be labeled by a configuration, a choice of G labels for each vertex. Since we're interested in fermionic models, there's also a fermionic degree of freedom. We place a spinless complex fermion at the center of each tetrahedron. The G cross Z2F symmetry acts in the following way. The G symmetry takes a configuration GV to a configuration GGV for some G and G. So it acts by left multiplication. This acts only on the vertex degrees of freedom and leaves the fermionic degree of freedom untouched. The fermion parity symmetry acts by acting with fermion parity, which I've denoted here by PT for fermion parity, on each tetrahedron. The fermion parity leaves the vertex degrees of freedom untouched. So there's our Hilbert space. Let me say a few words about the fermionic operator algebra, and then I'll give an explicit wave function, which is representative of one of these supercohomology phases. At a single tetrahedron, the fermionic operator algebra can be generated by the usual creation and annihilation operators. Alternatively, we could generate that same fermionic operator algebra using a pair of Majorana operators. We're interested, of course, in the full Hilbert space, and we actually only need to focus, for purposes of this talk, on the fermion parity even operator algebras. Fermion parity even operator algebra. This is right the whole time. This can be generated by two types of operators. The first, as you might expect, is fermion parity at a single tetrahedron, which can be written in terms of the Majorana operators like so. The second is what we've been calling a hopping operator. It transfers fermion parity between neighboring tetrahedra. So here's a picture for the hopping operator SF. It's defined for a face F, and it transfers fermion parity between the tetrahedra neighboring that face. So it acts with gamma on one tetrahedron and gamma prime on the other tetrahedron. And the choice of gamma versus gamma prime is determined by the orientation of the face. The hopping operator is also defined with a spin structure dependent sign. So we've included the spin structure dependence of our models through the definition of our generating set for the fermion parity even operator algebra. We, of course, don't need to include this spin structure dependent sign in the definition of the generators, but it cleans up our models to some degree. There's a very nice graphical interpretation of this spin structure dependent sign. If there's both interest and motivation at the end of the talk, someone can remind me, and I have a slide which has a pretty picture on it describing this sign. Intuitively, one of the consequences of this sign is the following. The parity and hopping operators are not completely independent. In fact, there's a certain product of hopping operators around a closed path, along with a product of undisclosed parity operators, which is equal to 1. It's identically equal to 1. And this holds only if we include this spin structure dependent sign. Heuristically, this says if you hop or transport a fermion around the closed path, then it doesn't pick up any signs. Now let me tell you about our supercohomology models. The wave function here looks kind of intimidating, but I assert that it has a nice, somewhat simple interpretation. So let me break it down. First of all, we have a sum over all the GV configurations on the vertices. So it's a superposition of these GV configurations. Here, vac is the fermionic vacuum. It's a state with 0 fermion occupancy. It's a +1 eigenstate of all the fermion parity operators. Next, let me focus on this green term. Remember, nu is valued in U1, so this is some phase. The product here is over all the tetrahedra. And what we have is for a fixed G configuration, we've weighted the tetrahedra by this phase. And it also depends on the orientation of that tetrahedron. If you're familiar with the group cohomology construction of bosonic SPT phases, then this phase might look familiar. The intrinsically fermionic part, and what makes supercohomology phases is this term in purple. What it does is it decorates a configuration with Z2F charges, with fermions, according to the G configuration. And it depends on the G configuration through the function rho. Naively, if you look at this product, you'd say it's ill-defined. That's because the hopping operators don't all commute with each other. So there's some ambiguity, there's some order dependence that I've hidden in this product. However, we also have defined a sign C here, which is order dependent. This product of hopping operators, it's a product over faces. This product of hopping operators is order dependent. The sign C is also order dependent. And it's constructed in such a way that together this full purple term is independent of any choice of ordering. So it's well defined here. So what does this state look like? What's interesting about this state? Well, I've said it decorates GV configurations with Z2F charges. This is in line with the generalized group cohomology understanding of the classification of SPT phases. To see that, let's just consider a single tetrahedron in this larger triangulation of an orientable three-manifold with a fixed G configuration. So there's G1 assigned to this vertex, G2, G3, G4. And let's just think about what happens when we apply the hopping operators corresponding to the faces of this tetrahedron. We might first act with the hopping operator corresponding to the face 2, 3, 4. This can potentially change the Fermion parity at that tetrahedron. It'll change it by a factor of rho, which has arguments 1, G2. 1 is just the identity in the group G. I should have mentioned that sooner. But it also depends on the G variables at the face 2, 3, 4. So it depends on G2, G3, and G4. Now we can consider the other hopping operators neighboring this tetrahedron. So we can act with the hopping operator corresponding to the face 1, 3, 4. And we pick up another factor of rho. And we can continue. So the hopping operator corresponding to the face 1, 2, 4, and the hopping operator for the face 1, 2, 3. At the end of the day, there's a fermion decorating that tetrahedron if this sum is equal to 1 mod 2. There's a nice property of the function rho. There's a constraint on the function rho, which I didn't make explicit. D rho is equal to 0. It's closed, which actually tells us that the fermion parity at the tetrahedron at the end of the day is equal to rho evaluated on G1, G2, G3, G4. And note that the homogeneity of rho, if those words make sense to you, the homogeneity of rho, I can multiply each of these arguments by some element of G and the value of rho is unchanged. The homogeneity of rho ensures that this decoration by Z2F charges is symmetric. So heuristically, what happens is there's a Z2F charge, a fermion, decorated on the zero-dimensional junctions of domain walls. So domain walls live on the faces of the dual lattice, and they meet at the center of this tetrahedron at a zero-dimensional point, at a point. And we decorate that junction with a fermion according to rho. So this is in line with the models defined by Wang and Gu, implicitly defined by Wang and Gu in terms of consistent possible decorations by fermions. But here the state is made explicit. So from here, we can do two things just to complete our construction of the supercohomology models. First, we can write down an explicit finite-depth quantum circuit directly from our choice of supercohomology data, rho and nu, that prepares this representative supercohomology state. There's something special about this circuit, and that is that it's globally symmetric. So this circuit, defined on a closed manifold, will commute with the global symmetry. However, this can still be a non-trivial SPT state, as Xiaogang mentioned, because these local gates are actually not symmetric. They're not G-symmetric. The circuit itself is symmetric, but it's composed of gates which aren't symmetric. And furthermore, for a non-trivial choice of supercohomology data, there's an obstruction to making those gates symmetric. It's indeed in a non-trivial fermionic SPT phase. What's nice about a symmetric finite-depth quantum circuit is that we can immediately write down an exactly solvable Hamiltonian. What we do is we find some sufficiently nice and trivial Hamiltonian let me call it H0, which in this case is some atomic insulator coupled with a decoupled and a decoupled G-spin paramagnet. It's an atomic insulator and a decoupled G-spin paramagnet. Let me also assume that H0 is symmetric and gapped. It represents some trivial fermionic SVT phase. And we can construct an exactly solvable Hamiltonian whose ground state is our representative supercohomology state by conjugating this trivial Hamiltonian, represented graphically here, by the finite depth quantum circuit labeled with rho and nu. So why is this an appropriate definition for an exactly solvable model? This Hamiltonian is symmetric because both H0 is symmetric and this finite depth quantum circuit is globally symmetric. This exactly solvable Hamiltonian is local because finite depth quantum circuits are locality preserving. The finite depth quantum circuit maps any local term in H0 to a local term of the exactly solvable model labeled by rho and nu. H rho nu is also gapped because the finite depth quantum circuit is unitary and preserves the spectrum of H0. So here we have it. We have an exactly solvable model for the supercohomology phases. What I haven't told you yet, and what I'd like to focus on the latter part of the talk, is that what's nice about these models, again, is that we can determine how the symmetry fractionalizes. We can see explicitly with these models how the symmetry fractionalizes on the loop-like Fermion fluxes, and that's a characteristic property of supercohomology phases. So that's what I'll talk about next. But before I do so, are there any questions, comments, concerns? Empty silence of the Zoom void? Anything?
Maybe as another trivial question, is the Kane-Milley insulator one case of this model?
Sorry, it's been a while. Kane-Milley is a topological insulator, correct?
Yeah, the trivial one that you introduced the talk with, the free fermion one.
So here, I'm not including any time reversal symmetries. And I'm not including any continuous symmetries. I've just assumed that the total protecting symmetry is a finite unitary symmetry times fermion parity.
Okay.
So maybe a more appropriate example here is by an atomic insulator, I mean, the Hamiltonian is the following. It's a sum of parity operators at each tetrahedron. So the ground state of this Hamiltonian will definitely be a product state. And in fact, it's the fermionic vacuum. It has 0 fermion occupancy, at least with a minus sign. It'll have 0 fermion occupancy at every site. So that's what I mean by an atomic insulator here. And a G-spin paramagnet is, instead of having a Z2 degree of freedom at a site, and a term that in the Hamiltonian just looks like a poly X, here I have a G-spin degree of freedom and some term in the Hamiltonian which projects onto a G-symmetric state on the vertex degrees of freedom.
So to follow up on that though, how hard would it be to extend these ideas to continuous symmetries? Time reversal, I assume, probably wouldn't be too hard, but continuous symmetries?
Yeah, that's a great question. I was planning on mentioning that in the open questions part of the talk. But here's what I can say. This framework works. You can just assume that the symmetry is continuous and you can try and do this construction just the same. The issue is, one, the Hamiltonian will have delta function-like interactions. And two, if we have a continuous group, naively by following this construction, you'd have an infinite dimensional site Hilbert space on the vertex, on the vertices. So there are some issues there. I think this naturally generalizes to the time reversal case, but there are some subtleties with the equivalence relation on the supercohomology data, and we haven't fully dealt with those. But with some slight modifications, just changing what it means to be homogeneous, I think this can be extended to anti-unitary symmetries.
But group supercohomology works for continuous symmetries, right, or not?
I don't know about the mathematical detail, but what I can say is that the Hamiltonian is kind of unreasonable. The model that you get out of this construction is kind of unreasonable because you have infinite dimensional Hilbert spaces.
I don't mean the model. I mean, like, does supercohomology still reasonably classify Fermionic SPTs in the case where the symmetry is continuous?
That's a good question. I don't know what sort of subtleties arise there, but I'm sure there are people in the audience that have written papers about such things. And I guess as far as I understand, the answer is yes, but someone should correct me if there are subtleties.
Thanks.
Let's move on.
Sorry, maybe a comment, a quick one.
Yeah, good, thank you.
I think we know already there's some phases with fermions that cannot be realized by local circuit. This is obvious, like, quantum Hall definitely is an example, right? Integer quantum Hall. So even though in principle one could do group cohomology to capture the transaminds term, in the action sense, topological reason, but those would not be directly applicable.
I would call integer quantum Hall an invertible phase. It falls outside of what I'm discussing here. You can't, as you said, you can't construct the ground state even approximately using a finite-depth quantum circuit.
Yeah, so.
Yeah.
Okay.
Maybe a more interesting example is boson integer quantum Hall with sigma xy equal 2 and thermal Hall conductance equals 0. Yeah, I don't know if there is any exactly solvable model for that. Maybe not.
Well, there may be, I think there are exactly solvable models. There may or may not be exactly solvable models, but a further question is, can you write down an exactly solvable model of this form, where the Hamiltonian, here's the other origin of disentangling in the title, where the Hamiltonian can be disentangled into some trivial Hamiltonian by a finite-depth quantum circuit. And in that case, the answer is no for the bosonic integer quantum Hall projected by some U1 symmetry.
I see that,
and that's
Kapustin and...
That's right, that's right. Under the assumption that the interactions are strictly local. That's right. There's no commuting projector Hamiltonian, and if you were able to disentangle a Hamiltonian like this, then you would be able to write down a commuting projector Hamiltonian, and they have a proof that that's not possible.
Do you also need to assume that the Hilbert space dimension is finite on each side, something like that? For that proof?
That's true, yeah, that's true, yeah. Thank you.
Tyler, I guess I missed it. You say if your framework apply to symmetries that are not a product of G and Z to F?
That's a good question. This again is on my open question slide. So we can just naively apply this to that case. We have to fiddle with the definition, fiddle with the representation of the symmetry, of course. And we were able to write down exactly solvable models in that case, but the symmetry has a somewhat unnatural representation. So the framework works just the same. There are issues with the equivalence relation. We can't show necessarily that the model we build is non-trivial, but we can write down a model. The problem is that the symmetry kind of seems ad hoc. It requires associating the fermionic degrees of freedom, which live on the tetrahedra, to certain vertices in a somewhat unsatisfying way. But we can indeed write down models for that case, yeah.
Okay, thanks.
And that's part of ongoing work, to write down models with a more reasonable symmetry action. Good, thank you for the questions. Everything on the slides can be found in the paper. So these questions are the new material. So here's our approach to understanding the universal properties of the supercohomology phases using our supercohomology models. And this follows some wonderful work by Ryan Thorngren and Anton Kapustin. Our strategy is to relate the supercohomology models to a particular bosonic SPT model via a series of dualities. Now, this isn't your usual zero form symmetry, SPT protected by a zero form symmetry. It's in fact protected by a two group symmetry, which loosely speaking can be understood as a zero form symmetry extended by a one form symmetry, at least for the purposes of this talk. So what I'll show in order to argue that these supercohomology phases indeed give us the universal quantized invariants that are characteristic of supercohomology phases is I'll start by describing how one can construct a two group bosonic SPT model from a choice of supercohomology data. You can then map this, it's dual to what's known as the shadow model. And finally, the shadow model is dual to our supercohomology models via fermionization, or the way I like to think about it in terms of fermion condensation. So there are three steps here. First, I'll write down a two group bosonic SPT model. Second, I'll show you what the shadow model looks like. And third, I'll give a heuristic description for fermion condensation with some nice pictures.
Can I just ask what you, how do I even just conceptually think about a zero form symmetry extended by a one form symmetry? How do the group relations work out? It means that if you start with a zero form symmetry, that some power of it suddenly looks like a one form symmetry?
Yeah, or some associator. Great question. Here's the next slide for you. So our two group bosonic SPT models are based on some models down by Ryan Thorngren and Anton Kapustin. They wrote down the gauged models of the models that I'm about to show you here, but morally all the content is in their paper. So here's how the two group bosonic SPT model Hilbert space looks. And then I'll tell you about the representation of the two group symmetry. At each vertex, there's again a branching structure. This is some arbitrary triangulation of an orientable three manifold. I've suppressed the branching structure just for clarity. We have a G degree of freedom at each vertex of the triangulation, as before, and also a Z2 degree of freedom at each edge. So the basis states in this Hilbert space can be labeled by a configuration of GV labels and a configuration of Z2 labels, which I've denoted by A. Here's how we can represent the two group symmetry acting on this Hilbert space. Part of the two group symmetry is parameterized by G and acts in the following way. On the G degrees of freedom, it maps a configuration GV by left multiplication to GGV. It also, here's the twisting up by a one form symmetry, it also acts on the edge degrees of freedom. So the configuration labeled by AIJ maps to AIJ plus some quantity determined by rho. So there's the part of the two group symmetry parameterized by the zero form G symmetry, by the group G. The two group also has a Z2 one form subgroup. This is an extensive symmetry group. The generators are extensive. There's an extensive set of generators. A generator generically looks like a closed sheet on the dual lattice in which you apply a spin flip. It acts on the Z2 degrees of freedom and all of the links intersected by that sheet. That's what a generator looks like for the Z2 one form symmetry. That's the Hilbert space and the symmetry action. Hopefully that somewhat clarifies your question, Ruben. The idea here is the usual group extension works with a two co-cycle. Here, loosely speaking, what I mean here by a group extension it instead uses a 3 cocycle. So if you're familiar with the construction of zero-form group cohomology models, then you know that you can construct an exactly solvable model from a choice of group cocycle. There's a similar story here worked out by Ryan and Anton. But in this case, you start with what's known as a 2-group cocycle. And I put this in a black box because I don't want to say anything more about it. And similarly, you can write down a representative wave function whose amplitudes depend on this 2-group cocycle. That 2-group cocycle is, it's very interesting. It's written explicitly in terms of rho and nu. You can also write down an explicit finite-depth quantum circuit, which is globally symmetric. And from that, you can write down an exactly solvable model. This is an exactly solvable model for the 2-group bosonic SPT phase. The next step in the construction in mapping this 2-group bosonic SPT model to our supercohomology models is to gauge the Z2 one-form subgroup of the 2-group symmetry. This proceeds in the usual way. It's a procedure that loosely follows the usual minimal coupling procedure, or a discretized version of that. We introduce gauge field degrees of freedom. These gauge field degrees of freedom live on the faces of the tetrahedra, along with a gauge constraint. We minimally couple, write down a gauge invariant Hamiltonian, and then try to fix the gauge in such a way that the Hamiltonian can be written explicitly and only in terms of the gauge fields. So the result of this is the shadow model, and the shadow model has a true zero-form G symmetry, which acts by left multiplication. So what we've done is we've mapped this 2-group SPT Hamiltonian to what's known as the shadow model by gauging the one-form symmetry. Since we gauged a Z2 symmetry, albeit a Z2 one-form symmetry, the shadow model, and it has a G symmetry, the shadow model is a symmetry-enriched Z2 gauge theory. Since we were gauging a one-form symmetry, for a one-form symmetry, the charges are line-like. The charges are line-like. So the gauge charges for the shadow model from this perspective are loop-like gauge charges. And the gauge fluxes are point-like. Now, one special property given this choice of alpha of this 2-group cocycle is that the point-like gauge fluxes have fermionic statistics. This is what will allow us to relate this shadow model to the supercohomology models. But first,
question.
Yeah.
So when you construct the 2-group SPT, you could have chosen somehow a different cocycle, but such that the charges become bosonic, or not?
That's right. Yeah, that's right. There's a special property of this alpha, which makes it so that there's an A cup dA term, if you'd like. And that's what makes it so that the shadow model has fermionic point-like excitations.
Mm-hmm. I see, thanks.
But you could remove this A cup dA term along with removing some extra stuff to make sure that it's a bona fide 2-group cocycle, and then you would indeed end up with bosonic gauge fluxes.
You would still use the same like H3 and C4 data, is that right?
That's right, yep. You'd still use that same input of a rho, because rho is used to define the 2-group.
I see, thank you.
So what's special about this shadow model is that the remaining G symmetry can fractionalize on the loop-like gauge charges. Let me give a heuristic picture for what I mean by that. What I mean is we can consider a state with a gauge charge, with this loop-like gauge charge. Then we can imagine acting with the global G symmetry on this state. It turns out this global G symmetry can be restricted to the vicinity, within the vicinity of the gauge charge. There's some equivalent effective symmetry action that acts only locally near the gauge charge. And if rho is sufficiently non-trivial, if we have chosen an interesting function rho, then this effective symmetry action has a nice property, which is this effective symmetry action is anomalous. It can't be written, there's an obstruction to writing it as an on-site symmetry action. There's an obstruction to writing it as a product of linear representations of the symmetry.
Question?
Yeah.
Is it enough to say that this effective action is not a product of on-site operators? I thought something stronger has to happen, like not only it's not a product of on-site operators, cannot be something like a symmetric finite-depth circuit acting on that line. Is that right?
That's right. Yeah, I'm being a little loose here. I guess the obstruction is I can't make this into a product symmetry, an on-site symmetry, via conjugation by a symmetric finite-depth quantum circuit, or by adding any lower dimensional SPT phases.
Okay.
But just to simplify things, I said there's an obstruction to be.
Okay. Thank you.
So what this anomalous symmetry action does, or one consequence at least, is it enforces some gapless modes to be carried by this gauge charge, or some symmetry-protected degeneracy carried by the gauge charges. And if this fractionalization is controlled by rho, so if rho is non-trivial enough, then this can't be removed by any finite-depth quantum circuit, and we have a non-trivial symmetry-enriched Z2 gauge theory. What we'll see is this is the characteristic property of supercohomology phases, and this quantized invariant, the symmetry fractionalization, can be pushed forward to our supercohomology models, thus showing that our supercohomology models have the right responses to probing with symmetry defects. And I'll make that clear in just a moment. I think I have just enough time to get there. So the last step we have, we've started at a two-group bosonic SPT model. We constructed a shadow model by gauging a Z2 one-form subgroup. The shadow model has this interesting fractionalization on gauge charges. It also has emergent fermions. The last step to construct, is there a question?
Yes, excuse. May I make sure, earlier slide, did you mention the gauge charge carry Fermionic statistics?
From this perspective, it's a gauge flux because we're gauging a Z2 one-form symmetry. It has fermionic statistics, that's right.
But sorry, but what's the dimension of the space or space-time in your model? Is it in general? Or is
This
it
is a 3+1. This is a 3+1 dimensional model. This is just a heuristic picture for fermionic statistics.
Okay, but sorry, but maybe this. Actually, I was going to ask another. Was going to ask different question, but right now you say something I need to ask again. But the gauge flux, sorry, in 3+1D, the gauge flux is should be a string and carried by some membrane operators, and the membrane operator, two-dimensional membrane operator ends as a one-dimensional gauge flux string in 3+1D.
So I've been a bit hasty here. Again, the gauge charge is loop-like because we're gauging a one-form symmetry. The charges of a one-form symmetry are line-like, so the gauge charge is loop-like. But maybe what you're getting at is if we instead go the opposite direction, and I was going to get to that here. If we go the opposite direction and instead undo the fermion condensation, or in other words, gauge fermion parity, or in other words, bosonize. So we start with our supercohomology model and instead gauge the fermion parity symmetry to end up at the shadow model. Then you're right. The fermion parity flux loops are loop-like. And the gauge charges, the fermionic, the Z2F gauge charges are point-like.
Okay, I think I get your point. But
okay.
I want to ask original question is that how do you check the Fermionic statistics? Just how do you see that? Maybe from your model. You claim the fact, but
yeah, that's a great question. So we can actually write down the emergent fermion string operators, and there's a lattice level prescription for computing the statistics when you have a string operator. This is part of the work done by recently. There's some work done by Levin and Wen on computing the statistics of anyons exactly on a lattice. And there's some more recent work that describes this problem with Kyle and Michael Levin. But the idea is you can compute two processes. I don't have a picture, unfortunately, so you just have to look at my hands wave. But you can compute two processes where you move an emergent fermion into a tetrahedron, then out of a tetrahedron, versus some other process which moves it out of the tetrahedron in another way and then moves it. There is a way to do it. I haven't described it well here, but there is a way to do it. It's in our paper. It looks like a tetrahedron with some red squiggly sticking out of it.
And moving in three-dimensional space.
Moving in three-dimensional space.
No problem. Does he also, just the last one, does he also carry some texture like a spin instead of exchange statistics?
Shall we maybe postpone the question to the end, because I'm kind of running out of time? Maybe Tyler can wrap it up and then we can have more questions.
Sure, let me just finish this story by doing the fermion condensation, and then I'll conclude. I'll flash the slide of the boundary construction so the fine people on YouTube can pause it and look at it at their own speed, and then I'll go to the open questions, and then I can address this. But I think I'll address this question on the way. So at this point, it's a bosonic model. The three manifold here needs to be spin. As far as I understand, that's guaranteed for an orientable three manifold. The spin structure enters in this next step. So again, what I'm doing is I'm showing that we can go from this shadow model to our group supercohomology models. And that can be done, at least heuristically, by fermion condensation. The way fermion condensation works is we can introduce bona fide physical fermions into the system and bind an emergent fermion with a physical fermion. The composite excitation is bosonic, so it can be condensed. We condense it by, again, introducing these physical fermions along with a gauge constraint, which proliferates the pairs of these composite particles. What does this do for us? Well, in this gauge constrained Hilbert space, we can replace a pair of emergent fermions with the bona fide physical fermions. These are all gauge equivalent pictures here, where what I've shown is you can replace the emergent fermions using this gauge constraint with physical fermions. You can then fix the gauge. You can fix a gauge in which all you're dealing with are these physical fermions. Everything's written explicitly in terms of these physical fermions. And what we've done is we've mapped from this bosonic model with emergent fermions to what happens to be a short-range entangled phase with the physical fermions. The spin structure enters only here. So the spin structure enters in writing down the hopping operator, that SF operator that actually nucleates a pair of the physical fermions. That's where the spin structure enters, and it's implicitly defined in the generators that we chose, and it doesn't appear explicitly in our wave function. Good, so let me wrap up. Here's the boundary construction. This follows some work by Wang, Wen, and Witten, which was worked out for the group cohomology classification of the bosonic SPT phases classified by group cohomology. Here we give a generalization to supercohomology models. And let me just finish with this slide, some open questions. Thank you for your attention.
Thank you very much, Tyler. A very clear talk. Maybe given the time, I'll just stop the recording here, and then if people have questions, they can just go ahead and ask them.